So kia ora katoa. My name is Shane Cronin. I'm a professor of volcanology at the University of Auckland in New Zealand. I've had quite a bit of experience in working around the Pacific in Fiji and Tonga, Solomon Islands, Vanuatu, and my main specialty is volcanic hazards, but I've also worked on seismic hazards and understanding how volcanoes work and understanding how we live with them and respond to them.
So in terms of the current volcano, can you give us, a bit of information about its size, its location, and also, the recent eruption events that have occurred over the last couple of weeks?
Yeah, so Hunga volcano was previously two small islands, one Hunga Tonga, Hunga Hapai, and these two islands are just the tips of a very large volcano that is underneath the ocean waves. And it's one of a series of volcanoes that is along a chain in Tonga. It stretches, actually the chain stretches from the northern part of New Zealand all the way up to Samoa. And there are a series of volcanoes that are underneath the water. Some of them are very deep and some of them stick out of the water, like Tofua, for example. But Hunga Hapai, Hunga Tonga were just poking out of the ocean, about 100 meters out of the ocean. Now they are on the edge of a larger volcano. So it's got a big bowl-shaped crater where those two little islands poke up from the edge. And that bowl-shaped crater is about 6 kilometers in diameter. And that's actually like the mother volcano. So on the side of this big mother volcano, on the edges of the bowl, there have been a series of small eruptions that have happened over the last few decades. And so we've seen small eruptions in 1998, in 2009, in 2014, 2015. And these have all been around the edges of that large 6 kilometer diameter bowl on top of the mountain, on top of the submarine mountain. And so our submarine mountain is about 1,800 meters high and about 20 kilometers across at its base. So it's a really big volcano, even though we can't see much of it. Apart from the small eruptions that it's had every now and again, and these small eruptions are not usually dangerous beyond the general area of the volcano. Sometimes they produce a little bit of ash that just goes harmlessly away into the ocean. But we know from the geological studies, when we look at the deeper history of this big volcano, that this big central volcano, the big bowl on the top of the volcano, produces eruptions about once every millennia. So once every 1,000 years or so, it produces these very large eruptions. And that is when enough magma has risen in and has stored into the volcano. And that's what happened a few days ago on the 15th of January, is the stored magma in the volcano erupted out of the big central crater rather than the small eruptions at the side. And this big eruption happened through seawater, and you think that water might stop the activity, but the seawater in this case was not deep enough to stop the activity. And instead, what happened when the volcano began to erupt into the shallow seawater, all of that magma interacted with the shallow seawater, and we had a very, very accelerated explosion. And the reason for that is the magma is 1,100 degrees C, extremely hot. And the water is only about 20 degrees C. So when the magma and the water come together, the water suddenly turns into steam. It just expands into steam. And when it does that, the water from a liquid to steam is a change in volume. It expands by 70 times. So basically, the eruption started, it was explosive, then all of that seawater got into the magma and in through the magma that was breaking apart in the first explosion. And when it did that, it really amplified the explosion and it became bigger and wider. And so on the 15th of January, that eruption lasted only probably around 10 minutes, but it actually blasted ash material all the way up to more than 30 kilometers high in the air. It also created a cloud of ash and gas that spread out sideways. And within less than half an hour of the start of the eruption, that big cloud had spread out across Tongatapu and had covered an area of around 350 kilometers, which is incredibly powerful. So the power of that explosion was very unusual. It was one of the most powerful explosions we've seen in the Southwest Pacific throughout modern history.
What does this mean in terms of, future scenarios being looked at or considered? And I guess, what are some of the current observations that you're seeing over the last couple of days as this evolves?
So what's happened now is, after this big eruption on the 15th of January, the top of the volcano has radically changed. We have seen that there were some other islands around the Hunga Hapai, Hunga Tonga, and there were some other islands that had formed in 2015, totally gone. There were some reefs to the south, also gone. Now, looking at satellite imagery now, we think that the top part of the volcano has sunk downwards. And it has done this because all of that magma has been removed from that eruption. So far, we haven't seen any disturbance in the water to indicate that eruptions are ongoing, although there was some reported disturbances in the first few hours after the main event. So we are currently thinking that there are two main scenarios for future activity. One of these scenarios is that the magma that was present on the 15th of January has now been exhausted by that large explosion, and that the volcano will settle down. The other scenario is that new magma will arrive to replace the initial magma that was exploded. And in that scenario, we're not expecting for it to have another very big explosion blast like the 15th of January, but that new magma should have an easier path to the surface. That means that the gas in the magma has a chance to escape and bubble out the top of the volcano as the magma is rising. That's like a safety valve. It means that we can have the magma rise into the volcano and then perhaps generate some eruptions, but we are expecting that if that's the case, the eruptions will not be as large or as violent as the eruption on the 15th of January. So those are our two scenarios. One is that settled down and we won't see much more from it. The other is that the magma has risen into the magma will rise into the volcano to replace the magma that was erupted away. And then we will continue to have a series of eruptions. Looking at the geological record, or the types of deposits that have formed in the eruptions that have happened in the past, there seems to have been several cases where there were a series of eruptions in a row. And when I say a series, I mean something like 12 or 10 eruptions in a row. And we can consider this a series as well. We've had three main eruptions, one on the 30th of one on the 30th of December of 2021, one on the 13th of January of 2022, and the big one on the 15th. So there could be further eruptions, and there could be further ash fall, and potentially also further tsunami in that scenario where the magma returns. So those are our two best guesses, and really it's only time that will tell which one is the right one, because we are struggling with monitoring the volcano due to a lack of seismometers in the area.
You touched on the tsunami risk. Are you able to shed a little more light on what that chance of future tsunamis is in the current scenarios that you're evaluating?
Yeah, that's a good question. So the current, one of the surprising things about the 15th of January eruption was the large tsunamis that were generated. They were maybe not so large in terms of wave height, but they dispersed a very long way. Now, these have not been very easy to predict because the normal tsunami models for these use an earthquake model. And so currently, the tsunami modelers are struggling to figure out what caused the tsunamis during that eruption. So with normal tsunami, there's earthquake motion, and so the floor of the ocean either lifts up or drops down, and that moves the ocean and causes a wave. With a volcano, if there's new material erupting at the top of the volcano, it can move the water out of the way as well. Or if the volcano drops down, like this one has, it can move surface water level drops as well, and you have a tsunami generated. So both of those things can take place. We can have the explosion pushing the water out of the way, or the volcano dropping down to push the water out of the way. Or even we can have a landslide off the front of the volcano, and that can also push water out of the way, and that makes a tsunami. So with volcanoes, the area that is affected is a lot smaller than with earthquakes. So earthquakes are very efficient at moving large amounts of seafloor up and down. Volcanoes are not, because the area of the volcano is quite small. And if you recall, I mentioned the crater on the top of the volcano is only 6 kilometers across. So if we drop that top surface of the volcano, it will create energy to make a tsunami. And if we have the explosion, it will create energy to have a tsunami. But that didn't explain how violent those particular ones were on the 15th. Now, we don't think that the future tsunamis from eruptions will be as violent as the 15th of January eruptions, but definitely when a volcano has new eruptions below the seawater, and suddenly new material is pushed out of the volcano, it will push the water out of the way and generate tsunami. They're very difficult to monitor for in this situation because we don't have seismic records near to the volcano. And the best pre-warning for any tsunami related to this type of volcanic eruption, and particularly for Hunga volcano, if there are new eruptions that create the sonic booms, the deep booming noises that many people heard across the region, if those noises are heard, or if there are so-called shock waves or air pressure waves that travel through the air and people can see or feel, if those occur, get to higher ground. Those are the best natural warning signals for a tsunami in the region.
Is there a reason why the tsunami wave didn't trigger the warnings or the sirens globally? You know, it's not just something that is specific to the region.
Absolutely. It's because the Pacific Tsunami Warning Center models and all of the models that we're using in different parts of the world, all of them are focused on the mechanism of sea floor change. So that is the earthquake mechanism. And with a volcano, in this case, there isn't any good seismic information on the size of the seismic equivalent of the explosion. So the models had nothing to trigger them. So because there's an eruption, the models automatically assume a normal volcanic type of event, and the tsunamis for a normal volcanic event are not very far traveling. Normally they stop after about 200 kilometers. So basically the problem is the overarching model that is used to trigger the warning has not seen one of these events before. And so now the tsunami researchers are very quickly trying to build a new tsunami model that can cope with this type of process. So it's pretty much science in progress, and they're running around trying to do that now, trying to figure out what went on and how they could provide a better warning in future, which is why I'm sort of reiterating that, you know, in the region, in Tonga and Fiji or elsewhere in the region, that in Vanuatu and anywhere that has an opportunity, has experienced the previous tsunami and also experienced the features, the things that went on before that. So people that might have heard the booming noises of the eruption, had seen some other signs in the waves prior to the eruption. For example, if the water drew down first, those are traditional kind of warning signs, natural warning signs. Those ones should be really paid attention to, especially vigilance over the next few weeks would be really important.
Moving away from the tsunami side of things and looking kind of more broadly, what impact could this activity have at other locations across the Pacific? So is it expected to increase volcanic and seismic activity at other locations?
Yeah, that's a good question. So it's commonly asked whether or not the eruptions of one volcano along a chain of volcanoes, for example, will affect other volcanoes on that chain. Well, what we can say is almost certainly not. So each volcano behaves with its own mechanism. And sometimes we have some coincidences when one volcano decides to erupt and another one does soon after, and people draw a process between that. But remember, we have thousands of volcanoes, thousands of them also underneath the ocean waves, but they generally have their own plumbing system. So they have their own source of magma that comes from deep in the earth and their own storage system for that magma. And so they all sort of also operate under their own cycle. So the Hunga volcano has this cycle of once every 1,000 years, it has a large eruption, and then in between it has a series of smaller ones. And so if you move to another volcano, it might have a faster or slower type of process operating it, but they do operate independently of one another.
Thank you. That's really interesting. One of the other areas that's being talked about a lot is areas around plumes, ash, volcanic gas, acid rain. What are these, I guess, is the first part of the question, and what impact can this have on communities?
Yeah, so we use the terms interchangeably. We use plumes, gas. You might even hear people use the word tephra, which is a word that's used to describe volcanic ash as well. But essentially, ash is broken up pieces of rock. Actually, it's usually very sharp and quite gritty. So very sharp little pieces of glassy rock. And ash is closer to the volcano, as usually can be quite coarse, can be even pebble-sized pieces. And then far away from the volcano, as the coarse material falls out, it is very fine-grained and it can be quite dusty. And it can get so fine-grained that you can breathe it. So that's ash, and ash tends to stay in the atmosphere for a number of days after eruptions, and it gradually falls out of the atmosphere. So it gets blown up into the air in an eruption plume, the wind disperses it, and it gradually falls out onto the ground. And the other part of a plume is gas. And so gas, including sulfur dioxide, water, carbon dioxide, and other gases that could include different elements like chloride and fluoride. These gases also float with the plume of particles, and as the particles fall out, the gases often stay high in the atmosphere. So currently, the plume from the 15th of January eruption from Hunga volcano is still in the air. The ash has mostly settled out, but the gases are still there and still remaining. They have been blown to the northwest, and they are currently blowing across the northern part of Australia and Indonesia. But there is a part of it that's kind of stretched all the way back to the Pacific. So those gases really travel a long way, particularly when they're blasted so high. And currently, one of my colleagues was telling me this morning that the plume is of those gases that are left behind, that is about 25 kilometres high at the moment, and it's travelling even higher than that as it heads over towards Australia. And so the problem with both gas and ash is when it comes down and falls onto and affects low-lying areas. So both the gas, both the ash particles can fall out, but the gas generally doesn't fall out by itself. It generally gets rained out. And so the gas gets dissolved into the raindrops and then falls down along with ash or after ash. And you might have heard the term acid rain. Well, acid rain is generated when water droplets are formed and rain is formed within within the gas plume.
That was actually my next question around, what impact does volcanic ash and acid rain have on food crops, for example?
Yeah, so this is where it starts getting really important, because ash and acid rain can have important impacts on food crops, but it's not all extremely bad news. So the main impact is this acidity. So the actual gas or the actual acid rain is not poisonous like you would expect, like it's not full of lead or mercury or arsenic or some kind of terrible poison. It's actually really quite acidic, and that's all it does. And so obviously plant leaves are badly affected by both ash and acid rain. And why I say both ash and acid rain is because when the ash falls down, and particularly if it's fine particles or if it's a bit wet, it sticks to the plant leaves, and then obviously the plant leaves can't get any sun and they die. But also worse than that, the ash has got the acid stuck on the outside of it as well. And so it tends to burn the plant leaves. So with some crops, imagine something like a green cabbage type crop or any type of green leafy crop, they're going to be badly affected. But if they have a root, so if it's a yam or it's dalo or taro or cassava, and it has a root to it, then the root of the plant won't be affected. It's just the leaves that are affected. So those crops and the root crops will still be fine, even if the leaves get burned. And particularly plants like ndalo or taro has an amazing resilience actually. And it's often because the leaves are kind of steep, they sort of hang down steep, and the ash can fall off them quite well. They're kind of shiny leaf as well. And I've seen people actually shaking them to get the ash off. And so I've seen that work very effectively in Vanuatu. So when ash falls onto the leaves of the taro and ndalo, if people go and shake that ash off, it really can fall off quite nicely. But sometimes if it's got too much water, it will stick on quite a lot. Maybe wait till it dries and then shake that off. So other plants like banana plants, as you know, they always fall down in cyclones and heavy winds and so on. When they're loaded with ash, they tend to fall down quite quickly. And also the banana, if they have some ripe fruit and the fruit has the acid on it, they are quite quickly spoiled. And so other crops that can be damaged are, any kind of market garden style crops like corn or chilies or any type of garden crop like that can be also quite badly acid affected. The ash is worse than the acid rain. So if there is ash, that is generally the biggest problem. And if there is no ash, but a little bit of acid rain, then it may be that the leaves first of all turn a bit yellow and then they recover. But if there is repeated acid rains, then there could be some more dying of the real green leafy plants. The key thing is how long plants are exposed to this acidity. So that's why when the ash is on the leaf, until the ash falls off the leaf, then the plants are exposed to that acidity and to that cover, and so they can be quite badly damaged. But acid rain, if it falls onto the leaf and then maybe a day later another rain comes along and it's a heavy rain, it can clean that off, and it also can clean off the ash if the rain is heavy enough. So that sort of nature can help to actually repair that damage. And it's all about how often the acid rain happens. So far what we're seeing is that a lot of the gas has actually gone from this plume high up into the atmosphere and heading over towards Australia. So we do not expect too much strong acid rain outside of the Tongan area. And even in the Tongan area, some of the skies have actually cleared quite well now. And the key thing to remember about acid rain is if it's a really little dripply rain, just a little bit of rain, a little misty rain or something like that, that's going to be the most strong acid rain. If it's a heavy rain, if it's a really downpour, that's going to be very dilute. So that wouldn't be the rain to worry about. The rain to worry about would be if it's just a small dripping of rain and you know that there's been an eruption recently.
What impact can the activity have on marine life? We've touched on food crops. What does this mean for fisheries and marine life?
Yeah, so near to the volcano or anywhere where there's a large amount of ash material into the water, that can cause a lot of fish deaths. And so if there's a lot of ash fall onto the water or the explosions around the volcano, that can produce that can cause a lot of instantaneous fish deaths because of the acidity and also because of these sharp little ash particles in the water, and they can kill fish. And so in general, if there are fish floating around that have died in relation to the ash in the water, those should not be eaten because it's not so much the ash that's the problem, it's the fish that die and then start to decay on the surface of the water. So those should be avoided. But apart from that sort of first impact when those marine, when the fish are killed by ashfall in some areas or killed by the volcanic material near the volcano, they will recover. Because basically what happens also is that when the ash falls onto the ocean, it adds actually some fertilizer to the ocean. So like your gardens, the ocean needs some fertilizer as well. And so particularly it adds a lot of things like iron to the ocean water. And the seawater is often a little limited in the amount of iron. And so that could generate a bloom of plankton, of microscopic plant life in the ocean. And then that sort of kicks along a cycle through the rest of the fisheries in terms of recovery and maybe a little boom of fish life following that. So it's not all bad news for marine life. In the first instance, possibly, but not later on. And the further you go away from the volcano, the less likely there's going to be any impact. So like I was talking about before, that the ash doesn't have any specific poison in it. It's mainly just a little acidic. It won't poison any other sea life that's still swimming around and happily surviving. So in terms of impacts on fishing, if fish are healthy, fish are healthily swimming around, no problem at all. And so other marine life as well is all pretty resilient to this. It's just nearby the volcano, or if there's very heavy ashfall into the ocean where fish deaths happen.
In terms of eating, crops that are affected, you talk about things like dalo and cassava and root crops, and you talk around fish. What's the advice around people consuming food in the current situation? Absolutely,
yeah. So the advice would be all the root crops like dalo, cassava, and yams and so on. All of these tubers, or if there are any potatoes or kumala or kumara or something like that, these will be fine to eat below the ground. They're absolutely fine. For any leafy crops, if there's any green cabbage or other types of leafy crops, if there's a lot of ash on them, essentially it makes it really difficult because it's very hard to clean off. So if they can be cleaned thoroughly, then they're safe to eat. But in general, the green crops are more trouble than they're worth to try to clean them. Unless there's a lot of water available, if they're covered in ash, it's safer not to eat them. With acid rain impact onto plants, they're still safe to eat. Again, a little bit of washing first, but it should be absolutely safe to eat, especially if it's been a heavy rain afterwards, no problem at all. Same for banana. If the bananas are nicely protected by the skin, if the skin has got some acid damage or ash damage to it, and that can be peeled away, the banana is safe to eat.
In terms of water sources, you touch on the water around food. What impact does the volcanic ash have on rainwater tanks or groundwater supplies more broadly? Should communities be concerned about the toxicity of drinking water, particularly with ash and acid rain?
Yeah, so with water supplies, groundwater supplies are generally not affected by volcanic ash or acid rain. They can have a slight lag in effect, but generally what happens is our soils are very good at filtering all of the acid out of the acid rain and out of the ash before it gets into groundwater. So groundwater, even relatively shallow bores, are usually very safe. And we've measured many of these in Vanuatu during eruptions, and we've seen that whilst the levels of some volcanic elements are higher in the stream or surface water, the groundwater is usually very safe. So that's the first, I guess, take-home message. Groundwater is not going to be affected. Second usual rule of thumb is that the main impact on water, even if ash or acid rain has affected water, the problem with ash is the fine particles. If they've gotten into the water, then you really have to let that water settle for the particles to get down and try not to stir it up. But in terms of the water, it's not going to be poisonous to drink. If there's no ash in it and it's just had a bit of acid rain, or if it's just had a little bit of ash and the ash has fallen out to the bottom, it's going to taste funny. So it may taste slightly metallic, but that is essentially because of the extra salts that the volcanic ash and the acid rain has put into the water. So now that's going to be still safe to drink, even if it is going to have that sort of salty or metallic flavor. So some children may be affected by that water and may get an upset stomach or something like that. And if that's the case, then moving to another source of water might be useful. But it's absolutely fine to continue drinking that, especially if there's only been 1 or 2 ash events. The difference would be if ash was coming every day. Ash was coming every day and affecting the water supply, then it starts to become a little more problematic. And not so much because it's poisonous, but it's just that ongoing addition of salts to the water is not good for long-term health. For short-term, no difference to drinking, say, a can of Coke or something like that. The chemical components in this in these waters make it a little acidic, but not as acidic as Coca-Cola, for example. So that's the sort of general rule of thumb around water. If you know that there is an ash fall is starting to occur, and you do have a roof fed water supply, then one of the safest ways to protect the water supply is to disconnect your pipe from the tank whilst that ash is falling. If the ash has fallen on your roof and your pipe is disconnected from your tank and the top of the tank is covered, the water in the tank will be totally safe. You can wait for the roof to be washed with rain, and then once it's clear again, reconnect the pipe, good to go. That's basically the way in which to live alongside ashfall or acid rain. Acid rain is harder to detect because it's a little bit more subtle, and the most best way of seeing whether there's been any acid rain is just the metallic taste of the water, or the green leafy crops will be showing some yellowing because of the acid burns.
This one is around past volcanic events and looking at fluorine. It's been a substance of concern, you know, with respect particularly to drinking water supplies.
Yep.
Is that the case with this volcanic eruption and this volcano?
Yeah, so fluorine is an element that's often associated with volcanic eruptions. So fluorine fluorine or fluoride is something that's all around us in our environments. There are no environments that we know of that do not have fluorine or fluoride. And it's a so-called essential element. So we all need a little bit of fluorine and fluoride, and it makes up parts of our body. It's within our teeth and in our bones and so on. And particularly for children, fluorine tablets are often taken, or in some places, fluorine is added into the drinking water. And that's because fluorine is essential for us to grow strong bones and teeth. And the problem sometimes happens in volcanic areas when there's too much fluorine. And that usually occurs when there are places where volcanoes are always erupting. So, for example, in the Southwest Pacific, places in Vanuatu have volcanoes that are always erupting. Yasua volcano is always erupting. Umbrum volcano is almost always erupting, and either it's erupting with ash or it's erupting with gas. And so in these places, there is a lot of fluorine and fluoride that gets into the drinking water and environment. And people get used to the higher levels of fluorine, and also there are ways in which that drinking water, for example, from groundwater is often less and having less fluorine than some of the rainwater. And also it depends on the time of the year, rainy season, dry season. But normally in other situations, when a volcano just comes to life and has an eruption and is erupting for a couple of weeks, there is not normally any problem with fluorine. The only problem is essentially just with the acidity in the water sometimes. So fluorine is an issue with volcanoes that last for a very long time, that erupt for years and years. If they erupt only for weeks to months, you know, the body can take that fluorine. It doesn't take it all in, and it can cope with that. And over the course of a normal year, you know, that would be absolutely fine. One thing a lot of people don't realize is that there's actually a lot of fluorine in tea, just normal black tea. And so it's a plant that has a lot of fluorine in the leaves. And so we are exposed to fluorine in different ways. And so in this case, in the Hunga volcano, the composition of the magma that was erupted is not especially rich in fluorine, and so this is probably a relatively low threat at the moment, particularly because there's only been really one reasonable sized eruption so far. Now, if these eruptions continue and there's long-term eruptions over years, then possibly there'll be some concern around fluorine. But like I said before, the groundwater is normally absolutely fine. And also, if there's very heavy rains, that's also very fine because it dilutes that fluorine down to very small amounts. If eruptions are only over days or weeks, no problem at all.
In terms of moving slightly more towards a bit more research and the fact that this has been identified as a 1 in 1,000 year event, or this recent eruption, I should say, can you explain what that means? But also, you know, does your research of the previous 1 in 1,000 year eruptions provide any information relevant to the current situation we're facing?
Yeah, so the reason why I mentioned that this volcano erupts with very large events every 900 to 1,000 years is that we have done some work where we look at past ash layers preserved within the sediments of lakes and swamps. So we drill through the lakes and swamps and we get the ash layers, and we can use radiocarbon dating on the material between the ash layers, and we can build up a history of this activity. Also, we can go to the volcano, and in this case, we went to Hunga, and we were able to see some deposits from the past eruptions that had pieces of charcoal and also pieces of coral within them. And so we can date the charcoal especially, and we can find out how often the big eruptions occurred. So that's the basis on understanding this 1 in 1,000 year cycle, because we've seen two major eruptions. One was around AD 1100, and another one was around AD 200. And then I've also seen some older ones in older radiocarbon dates going back to when the records began for me, which is around 6,500 years old. So in that case, we see that there's a regular pattern of activity at the volcano. Now, when we know that we're into a large explosion event, like on the 15th of January, then we look at those deposits from the past events, and we try to understand how many individual parts of that eruption happened. And when you're reading the geological record and you're looking at those deposits, it's an imprecise science. But we can say from looking at the deposits on Hunga, the past ones from the last big eruptions, there seems to be evidence for many separate explosion events, and maybe up to 10 to 12 explosion events in the last big eruption. And the previous one, maybe at least 3 or 4 big explosion events in that eruption. So we could be expecting to see for the current eruption that there are other explosion events that will continue the sequence. So we're looking now into that, and we haven't had a chance to be able to go to the volcano and check the deposits yet to compare them to the ones of the past. But based on the number of events so far, there seems to have been 3 big events so far, 2 smaller ones, 2 sort of medium-sized ones, and 1 very big one. We're using that as a kind of a basis to suggest that maybe some more eruptions will come.